Hi, my name is Duncan. Um, I worked in the New York State Center for Engineering Design and Industrial Innovation. Research mentor was Kim Lewis, but I worked exclusively with Professor Dr. Hume. And my research was into the integration of automotive instrumentation with motion-based simulation. So basically, the overview we will talk about today is when you talk about my topic more specifically, the background, what is mechatronics, what is simulation, my research goal, the methods that I use, the results I got, conclusion, and future work. So my top basic is use of mechatronics to help integrate instrument cluster with the motion-based simulator. So what is mechatronics? And basically mechatronics is a synergy of mechanical, electrical control systems, and computer engineering that is used to generate simpler, more economical and reliable systems. This synergy is used to create and design, manufacture useful products. So some applications of those products are in medicine, in electrocardiograms, and robotics, where the human control or autonomous. Also in the automotive field, where they use for dashboards, and electronics like TV, cell phones, and MP3 players. So what is motion-based simulation? Motion-based simulation is just basically a reproduction of the real world. It offers a safe and controlled environment so a human driver can take the place behind the steering wheel of a car that he is driving and handle it without concerning about dangerous and costly accidents. Also, it helps decrease research and development time. For example, computer-aided drafting and finite element analysis are also simulation modeling tools which help you reproduce products before they develop so you can make changes that are quickly and easy. And it aids in education, driver training, and gaming and research. So think of educating drivers how to use ABS systems within cars, how not to, how to maneuver vehicles in skid situations, or whether they're on snow or wet surfaces. So just an overview of what we just learned. So mechatronics is a multidisciplinary field, and we also know that simulation is able to replicate the real world. But why and how can we utilize the two in combination to achieve my goal? So we looked in the combination of the instrument cluster, which is a real actual instrument cluster from a 1999 Ford Contour. We wanted to add it to Nestle's motion-based simulator, which is in the basement, it's in the bottom floor furnace. And we did this using a microcontroller development board. So a research was done into the simulation design aspect of it, where we wanted to look into the necessary components of the instrument cluster, which we want to have functionally working. These things include, speedometer, tachometer, fuel and engine temperature gauges, and relevant indicator lamps. For example, like turning signals. We wanted to also look into additional display devices, either to help the driver interact with the simulation, or display information which cannot be displayed via the instrument cluster. So also research was done into the mechatronics side, and where we were looking into a development board which has either MCU, which is a microcontroller. Basically, that's a small computer on an integrated circuit, which contains a processor, memory, and programmer input and output peripherals. We also look into different specifications. So the more memory it has, the more programming you can put into it, and also if it has a lot of input-output pins so that it can be used to control different individual pieces of the instrument cluster. We also look at programming languages. Assembly is very close to what they call mnemonic code, which computer reads through ones and zeros. It is very low-level language, and the computer can read it quickly and perform the task very easily. But C and BASIC are more of high-level languages, which allows people to understand what is going on because it's more logical. We also look into three different devices. We were thinking about the TFT LCD, which is what you see in your GPS devices, because we were also considering a reconfigurative display, which means that you can add different components via programming, and you can change it and have it move in any form you want. We also looked into serial LCD and vacuum fluorescent displays, which are additional displays help display the extra information that the instrument cluster cannot display by itself. So, what did we come up with? How do we keep in mind the authentic user experience while implementing this instrument cluster? We noticed that all the gauges were necessary. The speedometer, tachometer, and fuel temperature gauges are all necessary because they're actual in real vehicles nowadays. Certain indicator lamps, for example, like the oil pressure light, the check engine light, and high beam indicator are not needed for the simulation. Also, the LCD wasn't chosen, and neither was serial LCD because the TFT LCD was too expensive, and also the serial LCD needed a backlight to be seen in dark situations because in the motion-based lab, it is in a very dark room, and they usually lower the lights so you can see the screen better. We chose the Action Development Board. A staff member who was working with is very versed with the board and has used himself, and he can quickly help program it and to control the instrument cluster. Also, the PC used to control the microcontroller itself was coded in C, which is a lower level language, which means it can be processed quickly. We need to be processed quickly because a user will detect if you're looking like you're doing 60 on a simulation, and your speedometer is only using 30. So how does all these systems work as a whole? We can see here, we start here, the PC controls the simulator, and the PC also controls the microcontroller. The PC controls this via the C programming language, and that development board controls the actual instrument cluster. So commands will come in C language, it will convert the C language into assembly, and assembly would output it to voltages which instrument cluster can understand, and that's how it moves back and forth. And then this information is displayed back into the motion-based simulator. So since the research is not fully completed yet, we're going to be looking into finishing the program algorithm for the PC controller. Basically, that is, what equations we use for speed and RPM. How does the gauges work? How do they work together? Also, the assembly coding for the instrument cluster handling. Assembly is not very popular, so it takes a little bit. It takes me a little bit longer to pick it up, and also with Roger Krupski helping me, the staff member that I mentioned before, he will help me to implement that program with the microcontroller. The instrument cluster itself has to be calibrated, and the voltages have to be determined. So we have to know how much voltage is needed to make the gauges say to move halfway versus full versus quarter way. In conclusion, with the integration, the Action Development Board was used to bring the PC and the automotive instrument cluster together with the motion-based simulator. We know that time delays that will detract from the user experience, so we need to work quickly. We want to provide realism, so we wanted the drivers to feel like they're in a real car. And we can do this when it has real components of a real car. That's why it's important for the instrument cluster to be implemented into the car. And this helps lay the foundation for future studies. One of the studies that they previously did was drivers' ADHD, and they use distractions like deer crossings and signals and other traffic to help study ADHD among drivers. And with the instrument cluster, the driver themselves can feel like they're immersed in their real environment, so that the results they obtain from the simulation could be more credible when the drivers themselves feel like they're in a real vehicle. Also, it does an aircraft dynamics course, which can help the instruments that we develop now can help use to develop further instruments for aircraft dynamic courses, where simulation can be used to help supplement labs and classwork. So that way you can actually feel what you're learning in the classroom. Here are some of my references. And I'd like to thank Nespity, a mentor, Roger Krupski, who's helped me a lot with the instrument cluster and the mechatronic side of it, and CSTEP, and all the staff and the interns. Any questions? Yeah, I drew it once or twice for a study they were doing for another class.
Oh, what conditions were you driving?
This one was just basically turning left and turning right and stopping at a light. The purpose of the driving wasn't really told to me, but um, I think he was trying to observe, I guess how far did I stop from the light, and how fast do I go when I see a turn coming up, and if I see traffic, a car slowing down in front of me, how quickly do I slow down myself and stuff like that.
So it's more of a test for you, or?
No, that was a separate project that they were doing when I drove the motion-based simulator.
What were some of the obstacles that you encountered throughout this whole process specifically?
One of the biggest obstacles I had was that the head researcher I was working under was not really into mechatronics. His field wasn't mechatronics, more of computer programming and simulation. So just finding what board to use or device to use help integrate the two instrument cluster and the motion-based simulator was kind of difficult. Relearning the program in C, trying to learn the program in an assembly language, trying to understand the components that were utilized along with the microcontroller that was in there, like different types of memory, and just try to understand all the specifics that goes along with it.
What's the timeline for your next step for the algorithms and the code?
Right now, I talked to Dr. Hume. He wants it done, if possible, by maybe the middle fall, early fall, and I'll continue working on it to finish all the way through. So probably by the end of the fall semester, I would say we'd want it to be finished.